Thanks for the introduction. So yeah, I'm going to talk about this new thing that we call trapdoor hash functions. And as I'm going to show really soon, it has lots of interesting applications. So let's start. And in order to give you some motivation, I'm going to actually begin with the application of a trapdoor hash. So all of our applications, they fall in the following context. We have a public function, f, that takes two inputs. And we have two parties, a receiver, Bob, with an input x. And we have a sender, Alice, with an input y. And the goal, essentially, is to let these two parties communicate. And at the end, we want that the receiver learns the output of the function on the two inputs. OK, so our focus for this talk is going to be on protocols that consist only of two messages. So at first, the receiver sends a message, and then the sender responds. And our goal is going to be to minimize the communication complexity of such protocols, or in other words, to minimize the length of these two messages. Good. So in an ideal world where Alice and Bob love and trust each other, we can construct very simple protocols that have optimal communication. But we're in crypto, so we're interested in a scenario where the parties do not trust each other, and each of them wants to keep his inputs private. And we're going to consider the semi-honest notion of security. And the main question we're going to ask is whether protocols that guarantee security can be as efficient as protocols from the ideal world. So in other words, we're asking what's the cost of security in terms of communication in such a setting. Perfect. So in order to give a meaningful answer to this question, we have to distinguish between two different cases. And the first case is when the sender's input is much larger than the receiver's input. And a very common and useful example is oblivious transfer, where the sender has two long messages, say of length n, and the receiver, Bob, wants to learn one of these messages. And we want to achieve this while keeping Bob's choice private against Alice. And we don't want to give any information to Bob about the other string, the string that he did not choose to get. So if we do not need security, then we can let Bob send his choice bit, x, and then Alice can respond with the chosen string. So the communication here is dominated by the length of the second message, which is n in this case. So our goal for secure protocols is going to be to optimize the length of the second message. And this means we want to optimize the download rate of a protocol, which we define as the ratio between the output length of the function, which is n in such functions, and the length of the second message of the protocol we're analyzing. Cool. So again, without security, we can get optimal download rate of exactly 1. So now we ask whether we can match that in secure protocols. And the bad news is that we cannot. And this is not surprising. And more specifically, we show that if lambda is our security parameter, then the length of the second message has to be larger than n by at least twice lambda. So the best we can hope for in some sense is download rate that at least approaches 1 when n grows larger and larger. And this is exactly what we get with a trapdoor hash. So let's see what we could do before trapdoor hash. So we could get a rate half oblivious transfer using generic assumptions. So these are protocols where the sender had to send at least 2n bits. And the only way to get a higher rate was to use high rate homomorphic encryption schemes. And the only such encryption scheme that was known is the Damgard-Yurik scheme, which with security based on the DCR assumption. So from all standard assumptions other than the DCR assumption, the best we could do is rate half oblivious transfer. And the only exception to this statement is two very recent papers, the one by Gentry and Halevi, the other by Brakersky et al., where they show how to construct optimal rate fully homomorphic encryption schemes under the LWE assumption. Good. So using trapdoor hash, we get the first optimal rate oblivious transfer protocols under the DDH, QR, LWE assumptions. And we also get a new construction from DCR with nicer properties compared to the Damgard-Yurik. So more specifically, we get statistical sender privacy in such protocols, and we get receiver privacy, which is computational under these assumptions. And the sender in such protocols, she sends n plus poly lambda bits in the second message. Good. So we can further get protocols for more general functions, such as a batch OT, batch OLE, and matrix vector product. Perfect. So besides rate 1 OT being interesting by its own, it also has lots of powerful applications. So the first application is in private information retrieval. Using our rate 1 oblivious transfer protocols, we get the first protocols for single server peer that have both polylogarithmic communication and optimal download rate. So we get the first such construction from DDH, QR, and LWE. And in particular, we finally solved the open question of constructing a peer with polylog communication from DDH or QR. The second application can be seen as a generalization of the above, and here we get homomorphic encryption scheme for branching program, where the length of the ciphertext grows only with the length of the branching program, but is independent of its width. And both of these applications are based on a transformation from the work of Isha and Paskin in 2007. In the third application I'm going to mention, we get the first optimal rate constructions for lossy trapdoor functions from, again, DDH, QR, and LWE. Good. So the second scenario I'm going to consider for our applications is going to be when the receiver input is actually the largest input of the two. And a very generic example is when Bob, the receiver, has a huge database of size n, and the sender Alice has a small RAM machine with running time much smaller than n. And the goal here is to let Bob learn the output of M when we run it on his database X. And notice that because the running time of M is much smaller than n, then in particular, when we run it on the database X, then it looks at very few locations of the database. So again, we want to achieve this, this functionality while keeping both M and X private. And there are lots of real-life applications for those of you who care. So without security, again, we can let Alice just send the description of the machine M, and this is very, and if we assume that M is small, then the communication here is independent of N and actually much smaller of N than N. So our goal for secure protocols is going to achieve communication that's somehow smaller than N. And this is already a non-trivial task when we restrict ourselves to protocols with 2 messages only. And another thing I want to mention is that if we want security, then we need to work in a model where we assume that there's a common reference string that the 2 parties can access. Okay, so before having trapdoor hash, the only solution to this problem that could get you sublinear communication was to use laconic function evaluation, where you would get communication proportional only to the running time of M. And this is in some sense optimal up to poly lambda factors. So laconic function evaluation would give you security under the LW assumption. And if lattice-based security was not good for you, then you could then another thing you could do is you could use a laconic oblivious transfer, which gave you more or less the same communication complexity and security based on the DDH assumption. However, the problem with laconic OT was that it would not guarantee the full notion of security. And in particular, the access pattern of the machine M is revealed to the receiver Bob. So using trapdoor hash, we get the first fully secure solution with sublinear communication and security based on number theoretic assumptions. So in particular, we get, using something we call private laconic OT, we get a protocol with communication complexity proportional to T times square root N under the DDH assumption. And if we want to use bilinear groups with pairings, then we could reduce that to cube root of N. And I'm already going to give you an open question, and it's whether we can close this gap between efficiency gap between lattice-based solutions and solutions based on assumptions like the DDH assumption. OK, so now that you know what are the applications of trapdoor hash, let's talk about trapdoor hash. And in order to define trapdoor hash, I'm going actually to begin with trapdoor functions that we all know. And I'm going to take you back to the 2-party context. So trapdoor functions allow some party Bob to generate a pair of a key and a trapdoor. And then Bob can publish the key, and in particular, send it to his friend Alice. And now Alice, given the key, can take her input X and evaluate the trapdoor function given this key and get some image Y. And the only one who can take Y and invert it back to X is Bob, who has the trapdoor. So using the key, you could evaluate the function, and using the trapdoor, you can invert it. So trapdoor functions allow Bob to recover the entire pre-image of y, x. And information theoretically, if he wants to do that, then he will have to see information which is at least larger than x. So y has to be at least as large as x here. However, in our applications, we need something a bit different. It's enough for us that Bob learns only a small part of x. We don't need him to learn the entire pre-image. But on the other hand, we want to minimize communication. And that's where trapdoor hash are useful. So trapdoor hash functions allow Alice to compute a very small image of her input x, which we call the hash value of x, and we denote it by h. And now Bob wants to learn only a small part of x. So let's assume he wants to learn the ith bit of x. So information theoretically, he's going to need something more than the hash value. So the trapdoor part of trapdoor hash functions will allow Bob to generate, again, a key and a trapdoor. And he's going to publish the key and send it to Alice. And now, given the key, Alice can compute a really small image of her input x, which we call the hint. And now only Bob, who has the trapdoor, can use this hint and the hash value to recover xi. So again, Bob recovers only xi, but he needs much less information, which consists of the hint and the hash only. So the syntax of trapdoor hash consists of 4 algorithms: the hashing function that takes the input x and the randomness r, the key generation, which allows Bob to generate a key and a trapdoor. We have the hinting function and the decoding, which inverts the hash value and the hint back to and recovers xi given the trapdoor. And we're going to require security for both parties. So we want that Alice's input x remains private, so the hash should not reveal any information about it. And on the other hand, we want that Bob's input I remains also private, so the key that he sends to Alice should not reveal any information about it. And our main efficiency goal here is, first, we want the hash to be small, and in particular, its size should be independent of n. And we also want that the hints are small. and in other words, we want that the rate of the trapdoor hash is actually high, where we define the rate as the inverse of the length of the hint. And to make some sense out of this rate definition, notice that Bob can generate multiple keys in order to recover multiple bits of the database. And you can see that the rate here, as we defined it, is asymptotically equal to the ratio between the information that Bob recovers and the length of the hints that Bob needs in order to recover this information. So the main technical contribution of our paper is constructions for trapdoor hash with optimal rate under the DDH, QR, LWE, and DCR assumptions. So next, I'm going to show you the trapdoor hash construction from DDH. And I want to say that we use techniques that were used before to construct schemes for IBE, laconic OT, and trapdoor functions with very nice properties. And we're going to work over a multiplicative abelian group G of prime order P. And we're going to have a public generator of this group, which we are going to denote by small g. And let's recall the DDH assumption, which says that if we take two random integers a and b from ZP, then g to the ab, it looks like a uniform group element, even given g to the a and g to the b. So let's proceed to the construction. So again, Alice has an input x, and the first we're going to have public parameters for our construction, and this will be 2n uniform group elements, which we are going to order in a matrix of 2 over n uniform group elements. So again, these are the public parameters, and now let's define the hash function. So the way that Alice is going to compute the hash is as follows. So Alice is going to go over every column in the public matrix, and she's going to take the top group element if the corresponding input bit is 0, and she's going to take the bottom group element if the corresponding bit is equal to 1. So she collects these n group elements, she multiplies them all, and get a hash value, which is essentially a group element here. So again, the hash value is defined as this product. And now she sends the hash to Bob. And like we said, we're expecting this hash value to be private. However, here we do not use randomness, so this hash function, of course, cannot be private, but you'll have to believe me that with a bit more effort, we can get statistical privacy for Alice. Okay, so now Bob wants to learn the ith bit of the database. And for that, he's going to generate a pair of a trapdoor and a key. And the trapdoor is going to be just a uniform integer in ZP, which we're going to denote by T here. And he's going to generate the key as follows. He's going to take the matrix from the public parameters, and he's going to raise every group element there to the power of T, the trapdoor. And then he's going to go to the bottom element at the ith column and multiply it by G. So the key looks like that. And we're going to denote the group elements there by the G tildes. And under the DDH assumption, we can show that the G tildes, they look like a uniform matrix even given the public parameters. And therefore, they hide the value of I from Alice. So now I want to show you how Alice can compute a hint that will eventually let Bob recover Xi. And the way she's going to do it is very similar to the way she computed the hash before, except now she's going to use the G tildes rather than the G's. So again, she's going to go over the matrix and take the corresponding group element from every column. She's going to multiply everything and get this group element, which is the hint, E. So again, we define it as this product. And we can already analyze the rate of this construction. So again, we define the rate as the inverse of the length of the hint. And we know that if we want a security from DDH, then the length of the hint has to be proportional to the security parameters. So roughly speaking, the rate of this construction is going to be 1 over lambda. OK, so now Alice sends the hint to Bob. And all it remains to show you is how Bob, given the hash, H, the hint, E, and the trapdoor, can recover the value of Xi. And I claim that all Bob has to do is to compare E to h to the t and h to the t times g. And Bob can learn the value of xi according to this comparison. So if E is equal to h to the t, Bob can conclude that xi is 0, and otherwise he can learn that xi is actually 1. And I'm going to convince you now why this is actually true. So let's assume for now that we define the g tildes as the tth power of the public group elements. So if the g tildes are defined this way, then it's easy to see that the hint is going to be equal to h to the t in all cases. Right? We just multiply the same group elements raised to the power of t. But in our construction, we do something a bit different. We actually multiply g tilde I1 by a factor of g. And now notice that the hash value is still computed as before, but the hint E now depends on whether we use the group element g tilde I0 or we use g tilde I1 in our computation of the hint. And this depends, of course, on the ith bit of the database X. So notice that if xi is 0, then we're not going to take this g factor. And if xi is 1, we're going to actually take it. And therefore, the element E is going to be always equal to h to the t multiplied by g to the xi. I hope I convinced you. So this is our trapdoor hash construction from DDH. But I promised you an optimal rate construction. And this is clearly not an optimal rate construction because the rate here is 1 over lambda, like I said. So what I'm going to show you next, or at least explain in a high level, how to optimize the rate of this construction and get a rate 1 trapdoor hash. Good. So our goal essentially is to take this hint, which is a group element, and compress it to a single bit. If we do that, we get a rate 1 trapdoor hash. But to keep the construction correct, we have to be able to distinguish between the compression of h to the t and the compression of h to the t times g, because otherwise Bob will not be able to make the comparison and learn the value of xi. So we want some encoding to a single bit that will distinguish between these two values. And the very natural candidate is to take the parity of the discrete log of the hint. Because notice that the discrete log of h to the t times g and h to the t, it always differs by 1, and therefore their parity will always be different. However, if we could actually compute discrete log, we could also break the security of the scheme. So this is inefficient, obviously. So the alternative to this is to use a very useful tool called distributed discrete log, which was first introduced by BGI in a totally different context. And distributed discrete log is actually an efficient algorithm, but it still satisfies the property we need. So what we essentially need is that if two group elements have discrete log that differs by one, then their encoding is going to be different. So the encoding that we're going to use is we're just going to take the parity of the distributed discrete log of our group element. And distributed discrete log, again, satisfies this property and will give us this inequality which we need for correctness. Okay, so with the time I have left, I'm just gonna give you some open questions. So again, to conclude, we introduced this new primitive. It's very simple and easy to realize using many standard assumptions. But on the other hand, it's super powerful. We get lots of new stuff we couldn't get before. And so we showed applications in two scenarios. And one can ask lots of interesting questions. And I think the more important question we can ask is whether these techniques and this primitive can be used to get other stuff. Yes, thanks for listening.
So we have time for a brief question, and the next speaker, please come to the podium in the meantime. So if there are no questions from the audience, I'll ask a question. So, you know, I'm fine with lattice assumptions, LWE, but so rate can be a critical issue in practice from an efficiency point of view. So are these techniques to reduce the rate something that is potentially interesting also in terms of practical performance of these schemes?
So we get communication that's like really, really tight, that really, so we get rate 1, but the extra bunch of bits that we pay are actually they're actually few in many of our constructions. I'm not sure I can say that the computational complexity can match the practical requirements, but speaking of like communication, the constructions are
which is already good. But do you think there is a potential for these techniques to lead also to something that people may want to run?
It's a good question. One has to think about it.
Okay, so let's thank the speaker again.